Okay, this video is on backward induction. We're going to talk about how to solve any game via backward induction. It might not seem like it, but one day this video is going to save you thousands of dollars. You lift weights to become strong. Well, we do these types of games so that we make good decisions, and good decisions are worth a lot of money. So this is a typical backward induction type game. And so what's important is that things are happening in sequence. Player one goes, then two goes, then one goes. And that describes a lot of the situations we face in everyday life. Um, this is not natural for us. We always want to start with the first player. Player one's going first at the top, and we want to ask, what should he do? What should player one do? And I don't know. It's complicated, right? Lots of stuff is going on here. I don't know what player one should do. So the goal is to train ourselves before we ask, what should player one do in his first move, to instead ask, what's going to happen? With each thing player one could do, what's going to happen? And so backward induction is just a fancy way of saying start at the end and work your way back. That's all it means. So we're not going to start with one's decision on top. We're going to start with one's decision on the bottom. So I find things still look complicated when I look at them. We've got two, we've got one that's hard to distract us. So I actually even prefer to just write on the side, just write down what one's last decision is. So this is what it looks like in my slides, and even this is too complicated because I've got the payoffs for one and I've got the payoffs for two. But this is one making the decision, and so one only cares about their own payoffs, which is the first number. So this is the way I'd like you to write it on the side. This is the last decision one faces. And now this is the world's easiest game. One can go left and get 0 or go right and get 1. Well, one should go right and get 1. Okay, so that's the backwards part. Backwards is we're starting at the end and figuring out what's going to happen. At the very end of the game, one is going to choose right and get an outcome of 1. The induction is using this information collapsing, forgetting about how it came about, and just realizing that the outcome of the last decision is one going right. So when we look at our initial game, we were looking at this last decision that we were looking at, and we've already figured what's going to happen, which is that one's going to go right, and the outcome is going to be 1, 3. So the induction part is just collapsing this. Instead of having this kind of complicated game, we're just going to write down that the outcome is what we've already figured out. We know that the outcome is going to be 1, 3. So this is everything. This is the magic, is going from that previous graph to this graph, which is to say we've just greatly simplified things. We've figured out at the end, if 2 goes right, the outcome is going to be 1, 3. So let me go back and forth one more time just to try to drill this in. The actual game looks like this. But we've already determined that the outcome of the last decision one will make is one will go right, and the outcome will be 1, 3. So we're just going to simplify a game with what we already realize is going to happen. If 2 goes right, the outcome is going to be 1, 3. And now we just do this again. So now we have a sequential game. We start at the end. We start at the last decision, figure out what's going to happen. So the hardest part of this is just keeping straight whose payoffs are who. Now we have 2 making the decision. 2 can go left and get a payoff of 2, or 2 can go right and get a payoff of 3. Well, 3 is more than 2, and so what 2 is going to do is 2 is going to go right and get a payoff of 3. So that's the backwards part. We've figured out the outcome of that little decision. 2 is going to go right. And the induction part is then just collapsing this and just replacing the decision with the outcome. So when we do that, one now has realized if they go left, the outcome's going to be 2, 1, and if they go right, the outcome's going to be 1, 3. Well, one is facing a choice between 2 and 1. 2 is better than 1, so 1 should go left. So let's summarize all that we've figured out. We figured out at the end, 1's going to go right, 2 is going to go right in the second to last decision, and so in the first decision, 1's going to go left. And we've just solved for the equilibrium of this game. We've figured out when everybody's acting optimally what's going to happen. And so now the last step is just to write down what the Nash equilibrium of this game is. And believe it or not, this is actually pretty hard. People mess this up, which is that every part of you is going to want to say, well, what happens in this game is one goes left and ends the game. Okay, that's what happens, but that's not the Nash equilibrium. The Nash equilibrium is a strategy for each player, such that nobody has incentive to deviate. A strategy is their whole plan. Everywhere where they could move, what decision could they make? So one strategy is actually left, right. And this tends to be a little confusing for people. It is confusing. right? Because one strategy, it's hard to even express this in words. What one saying is, my plan is I'm going to end the game and go left. But if I went right, and if two went right, then my plan is to go right. Right? So just accept it's a little uncomfortable, but this is what it is. Everywhere where you could make a decision, what decision? What's your plan? Okay? Two's is a little simpler. Two's plan is that if they move, they're going to go right. And that's it. That's how you solve any game via backward induction. You start at the end, you figure out what's going to happen, and then you use that information to just simplify the problem. Instead of worrying about how it came about, you just write down what you know the outcome's going to be, and it makes the decision-making process much simpler.